Hi, I'm Chongai Kuang, the Site Science Team Lead, and along with Sean Serbin and Scott Giancrande, my co-PIs, and the rest of our Site Science team, I would like to present our science and deployment plan of the DOE 3rd Atmospheric Radiation Measurement Mobile Facility in the Southeastern United States. In terms of the outline for this talk, I'm going to present a little bit of background on why the 3rd ARM mobile facility is moving to the Southeastern United States. I'll then present summaries for the Southeast US relevant science drivers for the deployment across the convective, aerosol, and land-atmosphere interactions processes topical groups. I'll provide updates on our pre-deployment activities focused on developing and applying science-driven criteria for preferred siting, site configurations, and measurement priorities. And then lastly, providing opportunities for you to engage with our site science team on these and other topics. ARM is relocating the 3rd ARM Mobile Facility, or AMF3, following recommendations from a DOE-sponsored community workshop that identified the Southeastern United States as a region with abundant surface force convection, large amounts of vegetative biogenic emissions, and strong surface-atmosphere coupling. A 5-year deployment is expected, with operations beginning in March of 2023. Our site science team is tasked not only with providing guidance to ARM regarding site selection and deployment, but also with developing an initial science plan that can be addressed by an AMF3 deployment to the Southeast United States. Our initial science plan comprises 3 interconnected topical areas: aerosol processes and properties, led by me, convective clouds, led by Scott Giancrande, and land-atmosphere interactions, led by Sean Serbin. Along with our leadership team, our core team membership includes Jim Smith, Allison Steiner, Gregory Elsasser, John Peters, Mariko Owe, Thijs Huus, and Pierre Gentine. Our core team comprises scientists with expertise and cross-cutting expertise across these topical subgroups of aerosol, convection, and land-atmosphere interactions. This is not a comprehensive list, but representative of who we have made outreach to so far. Our outreach extends beyond ARM and includes engagement with the environmental systems science community, Southeast US experts such as leadership within the SEUS measurement campaign and partners at the University of Alabama at Huntsville and at Tuscaloosa, Southeast US measurement networks, including those from NASA and Ameriflux, the United States Forest Service within the region, and also Southeast US measurement campaigns such as Vortex Southeast. Within these 3 topical areas, we have a number of targeted cross-cutting science drivers that include the onset of convective clouds, deep convective properties and processes, aerosol optical properties, aerosol controls on the budget of cloud condensation nuclei, and land-atmosphere two-way interactions, including strong coupling of land surface with atmospheric processes, influence of regional heterogeneity on land surface modeling, and surface dynamic controls on regional aerosol. Some of our convective cloud science drivers include topics related to convective cloud onset, including large-scale versus mesoscale thermodynamic perturbations, processes that regulate shallow to deep convective transitions, and the role of moist thermals. There are also topics related to convective cloud processes, including the relationship between boundary layer coverage and convection, the nature of convective updrafts, and convective organization and stratiform precipitation. Some of our aerosol science drivers include topics related to processes and properties that control the budget of cloud condensation nuclei, including new particle formation and transport, biogenic and anthropogenic controls on secondary organic aerosol, spatial and temporal variability in the water uptake properties of aerosol, and topics related to aerosol optical properties, including particle water uptake, biomass burning, and brown carbon. Under our land-atmosphere interaction science drivers, there are topics focused on the process-level coupling between land and atmosphere, impacts of a surface heterogeneity on that coupling, and identifying the land surface biotic and abiotic controls on surface fluxes and energy budget, shallow to deep convective processes, and aerosol formation. There are also topics focused on turbulence and boundary layer measurement and modeling, and two-way interactions between plants and cloud aerosol radiative impacts. Okay, so now that we presented a high-level overview of what we hope to study and achieve with an AMF3 Southeast US deployment, I would like to present our timeline, plan, and activities related to deployment of the AMF3 in the Southeast United States. So beginning with the planned start date for site operations in spring of 2023, and given the time it takes to complete environmental reviews and prepare a site, we are looking at the site being identified in September of 2021. And given the amount of time it takes to select a site from a short list of potential sites, our site science team delivered a siting guide in March of 2021 to ARM leadership and our site operational partners. This siting guide provides recommendations on not only potential sites, but also possible site configurations and measurement priorities. Our site science team has been actively working on developing and applying science-driven criteria across the aerosol, convection, and land-atmosphere interaction topics for preferred regions for siting, site configurations, and measurement prioritization and sampling considerations. So our team is currently soliciting feedback from you, the community, on potential site configurations and measurement priorities that are needed to address the important science questions and drivers in the region. I'll now present some examples of spatial analysis that we've done so far related to siting and site configuration. And here's a high-level summary of the siting criteria that were developed. Our science drivers prioritize avoiding coastal regions, representative and low complexity terrain, representative forested sites, representative air mass sampling, representative convective cloud frequency and diversity, allowable airspace for aerial observations, and proximity to preferred observational network partner facilities. Our science drivers prioritize daytime convection, surface-driven cloud aerosol processes, convective cloud transitions, and synoptically driven deep convection, all of which point to a focus on the interior Southeast United States. We also have a preference to site in a region with representative cloud frequency and diversity. Here is a map of the June through August cumulus cloud fraction, defined as the percent of time over a 24-hour period as derived from GOES satellite observations. We also have a strong preference to site in an area with representative and low complexity terrain. So here's an exclusion map of the Southeast US that shows areas that meet preferred specifications for terrain complexity. A strong preference for sites in relatively flat locations with low slope and low roughness. In this map, the white areas meet our terrain complexity requirements. Our aerosol science drivers strongly prefer regionally representative sampling, where it is desirable to have contributions from both urban and natural environments to study the role of anthropogenic and biogenic emissions and their interactions on aerosol properties and processes. Preferred siting regions could be characterized by exposure to a regionally representative range in anthropogenic emissions, as an example here, NO2, and biogenic emissions. The map here illustrates the annual column maximum value NO2 map from Tropomi and TMIS retrievals with regional NOAA National Weather Service NEXRAD locations in black circles and the associated radar ring buffers. The NEXRAD network is an example of a potential Southeast US partner operational observational network that could enhance site measurement capabilities for science drivers that, in this case, cross-cut aerosol and cloud topics. And here is a spatial analysis example that cross-cuts the aerosol and land-atmosphere interaction topics. This example is motivated by the science question: what are the roles of isoprene and monoterpene emissions on the diurnal, seasonal, and spatial distribution of secondary organic aerosol? Example citing criteria that flow from this science question include citing in a region with sufficient emission of isoprene and monoterpenes. And a map that helps to inform on that criteria is shown on the right, an isoprene emission factor map from the Megan model. Hotter colors in red are areas of higher emission, and cooler colors in blue are areas of lower emission. Several Southeast U.S. science drivers require sites having a minimum contiguous area of similar forest vegetation composition and plant structure. A larger forested main site is preferred, depending on final deployment configuration, having sufficient canopy cover. Remote sensing and GIS tools provide larger scale guidance for siting based on science requirements. But for specific candidate sites, detailed image analysis and in-person assessment will be needed. Additional land-atmosphere interaction considerations depend on the dominant species type. Overall, forested sites should not be fragmented by large roads, rivers, ponds, clearings, or breaks, as in fire breaks or power lines. The maps above illustrate the land fire 30-meter canopy cover products in the upper panel and forest canopy height products in the lower panel, subset to the larger Southeast U.S. region. We are also analyzing a combination of remotely sensed data with regional land surface model simulations across the Southeast U.S. An example of model data that we plan on using is shown on the right, a map of total latent heat flux. Other key considerations in spatial data of interest include evapotranspiration and soil moisture patterns, the distribution of plant composition and structure, vegetation seasonality, and how these considerations link surface with cloud and aerosol data. We've also been doing a lot of work in mapping out our science drivers to the corresponding instrument requirements needed to address that particular driver. Here is an example where the table on the right presents a subset of our land-atmosphere interaction science traceability matrix and corresponding instrument requirements. In the first row, you can see how the science driver of understanding land surface carbon, water, and energy fluxes maps onto corresponding measurement requirements, then on to instrument requirements, and then on to functional requirements. So as an example, here, specifications on required measurement platforms. The image on the left is of a flux tower in the Talladega National Forest, an example of such a measurement platform that is motivated by these science traceability matrices. Our site science team is also making recommendations to ARM regarding configuration of boundary facilities and desired measurement and instrument capabilities at these potential boundary facilities. Our recommendations have included at least 3 non-collinear profiling facilities with a configuration and spacing sufficient to characterize effective tendencies. We've also made recommendations for advanced LiDAR, multi-sensor atmospheric thermodynamic profiling, cloud sampling and imaging, cloud and precipitation from scanning and surveillance radar, and aerosol size distribution, chemical composition, and water uptake measurements. While we are still in the pre-deployment phase of this project, our team is dealing with some persistent pre-deployment considerations. These include balancing fine-scale requirements for effective tower siting with respect to surface measurements, while also satisfying connections with larger scale atmospheric processes. The scale and type of heterogeneity in the Southeast U.S. is also a persistent consideration. As mentioned before, we will need more than one site to sufficiently characterize regional signals and patterns and contextualize surface point observations. ARM has always sought community feedback. This provides opportunities for continuous improvement, flexibility to identify high priority science needs. These are often gathered through workshops, working groups, field campaign PIs, and other mechanisms. As a team, we strive for a very active community outreach. This includes outreach to ARM, atmospheric system research, environmental system science, relevant multi-agency Southeast US field campaigns, Southeast US experts, partners, and measurement networks, and you. We have a Slack channel, an email list, and a webpage in order to gather your feedback. Thank you.